Hello viewers, welcome to my channel. If you are new to this channel, kindly make sure you subscribe, you like and share the video. And if you are here to watch the previous lesson, kindly make sure you go through them before moving to this particular lesson. In today's lesson, we will be discussing about independent events and theorem of total probability, that is total probability theorem. So first we will discuss about independent events. Independent events. So the theorem of an independent event says that if two events A and B, that is, it has two events A and B. Say two events A and B are independent. If they are independent, if the conditional probability of A given B is equal to the probability of A, and the conditional probability of B given A is equal to the probability of B. So if these two things are satisfied, definitely the two events are independent events. And if those two conditions are not satisfied, it means it is otherwise. That is, they are dependent. They are dependent. So if this situation, if these conditions state that the conditional probability of A given B is equal to probability of A, and conditional probability of B given B is equal to probability of B, definitely our formula can be modified. It could be called from the conditional probability, which says the probability of A given B is equal to the probability of A intersection B over the probability of B. Definitely our probability of A intersection B will be equal to the probability of A given B multiplied by the probability of B. And if A and B are two independent events, that is, the probability of A given B is equal to probability of A, definitely the probability of A intersection B is equal to probability of A multiplied by the probability of B multiplied by the probability of B. So that's what the theorem of independent events says. So let's solve an example on that. Example 1. So the example says a box of fuses contain 20 fuses. A box of fuses to contain 20 fuses. Automatically, the number of sample space n of s will be equal to 20, of which 5 are defective. And it says if 2 fuses are selected at random and removed from the box in succession without replacement, that is what is trying to say in succession is that one is removed before the other is removed, that is in succession, without replacement. So we can let A be the let P of T be the probability that the first fuse is defective. So we can say let P of A equals to the probability that the first fuse is defective. And let P of B equals to the probability that the second fuse is defective. And the question says a box of fuses contains basic fuses of which 5 are defective. Initially 5 are defective. If 2 are selected at random, if 2 fuses are selected at random from the box in selection without replacement, the question now says what is the probability that the fuses are defective? That is, the 2 fuses are defective. Let's try to tell you that find the probability of the first fuse is defective and the second fuse is defective. Then definitely what are we looking for? We are looking for the probability of A intersection B. We are looking for the probability of A intersection B. So to determine the probability of A intersection B, and these two events are independent events because they are removed in succession. That's why they are independent events. One is removed without replacement, while the second is removed. So the probability of A, the probability of B will be, initially it's having 5 defective fuses. 5 defective fuses, and the total sample space is 20. Definitely the probability that the first is defective will not be what? Will be 5 over 20. Will be 5 over 20. So the probability that the second is defective, probability that the second is defective, which is probability of B, will now be what? The number of defective fuses has been reduced to 4 because initially we were having 5 defective, but one has been removed without replacement. They didn't replace it. I didn't know it was replaced, then we will still be left with 5 defective. But one has been removed, definitely we left with 4. Which can be defective. So definitely this will be what? 4. And also don't forget the total number of fuses will also have been reduced by 1 as well, which will now remain what? Which will remain 19. So we have 4 over 19. So the probability of A will be 5 over 20 and probability of B will be what? 4 over 19. So we now want to determine the probability that both fuses are defective. That is, the first is defective, the second is also defective, which is the probability of what? Of A intersection B. To determine the probability of A intersection B, the two events are what? Are independent. So we can apply the formula we have where which says it is equal to what? The probability of A multiplied by the probability of B. We have derived that here. So we said the probability, the functional probability of A given B multiplied by the probability of B is equal to the probability of A intersection B. And since the two events are independent, then the probability of A given B will reduce the probability of A. So definitely this becomes 5 over 20 multiplied by 4 over 19. And if you do that very well, you will be left with 1 over 19. 1 over 19. 1 over 19. Because 5 times 4 is 20. 20 cancels 20. We are left with 1 over 19. And that's that. Example 2. And the second example we need to be solving, I want it to be under the second aspect, which is the aspect of theorem of total probability. So let's quickly move to theorem of total probability. Theorem of total probability. So with this first example, we should be able to tackle any question as regarding the aspect of independent events, since we've understood the concept. So theorem of total probability. So the theorem of total probability, what does it say? It says if event B1, B2 up to infinity, up to bk, let's say bk, where k can be 1, 2, 3 up to any point in which as the case may be. So it says if it's a portion in a sample space, if it is partition of the sample space, that is, if it is part, if they are all parts, if all these events are all parts of a sample space S, if they are all parts of a sample space S, comma, where the probability of PI is not equal to 0. What does that mean? I really don't something, like we've done in the previous lesson. And when we represent those things by I, what we are trying to say is that I can be 1, it can be 2, it can be at least 10 here, that is I plus 1, 2, 3, and so on. That is the probability of each debate is not equal to 0. Is not equal to, that's the condition. Comma. Then for any event A, of that sample space S, then P probability of A, which is the total probability. What it's trying to say is that B1, B2, B3, and the likes all contribute to the total probability, all contribute to event A, and they all belong to sample space. A belongs to sample space S, B1, B2, B3, and so on also belong to sample space S. So the total probability of A will be given as the probability of B1 multiplied by the probability of A given B1 plus the probability of B2 multiplied by the probability of A given B2 plus the probability of B3 multiplied by the probability of A given B3, and so on. So everything, all the events here, B1, B2, B3, and the likes all contribute to the total probability A. So the probability A cannot be derived from this formula. That is the probability of B1 multiplied by the probability of A given B1 plus probability of B2 multiplied by probability of A given B2 plus probability of B3 multiplied by probability of A given B3. So that's the formula. So let's now apply that in an example. So the example we are having here, the example says bowl B1 contains 2 red and 4 white chips. Bowl B1 contains, let me read the question. Bowl B1 contains 2 red and 4 white chips. Bowl B2 contains 1 red and 2 white chips, and bowl B3 contains 5 red and 4 white chips. Then we are given the probability for selecting the bowls. That's the probability of selecting bowl B1, which will be equal to 1 over 3, probability of selecting bowl B2, which is equal to 1 over 6, probability of selecting bowl B3, which is equal to 1 over 2. Then we have to find the probability of drawing a red chip. Which is the total probability, because each bowl contains a red chip. So all the bowls are contributed to that red chip. So the probability of drawing a red chip will now be the total probability. So what the question says, it says bowl B1 contains 2 red. Bowl B1 contains 2 red and 4 white chips. 2 red, 4 white. Bowl B2 a B2 contains one red and two white tips. The B3 contains 5 red and 4 white tips. So what is the total number of chips? The total number of chips, 5 plus 2 plus 4. The total number of chips sums to 18. The total number of chips sums to 18. So the total number of chips which is the total number of sample space, NS, is equals to 18. So to determine the total probability, that is the probability of drawing a red chip, which is PR, let's represent that as PR. From the formula of total probability, what will we have? We have the probability of B1 multiplied by the probability of A of R in this equation is going to be R, because we are looking for the total probability of drawing a red chip. R B1 plus the probability of B2 multiplied by the probability of R giving B2 plus probability of B3 multiplied by the probability of R giving B3. So to determine the probability of B1, to determine the probability of R giving B1. So we are given the probability of B1. Mind you, we are given the information in the question. The question says the probability, I read it before I started solving it. So the probability of B1 were given to be 1/3. This one was given in the question. The probability of B2 were given to what? 1/6. And the probability of B3 was given to be what? 1/2. So we are plotting probability of B1, probability of B2, probability of B3. So you can easily plot this one into our formula. But we don't know the probability of red given B1, probability of red given B2, probability of red given B3. So to determine that probability of red given B1, if you recall from the conditional probability, this one definitely equals to the probability of red intersection B1 over probability of B1. Remember, over the probability of B1. And this can be determined from our information here and our total number of sample space. We can determine it from that. So how do we determine probability of R intersection B1? Probability of R intersection B1. That is the probability of red chip inside B1. How many red chips are we having in B1? We are having 2 red chips. What's our total number of sample space? Our total number of sample space is 18. That's automatically 2 over 18. That's automatically 2 over 18. So to determine, we've gotten it to be 2 over 18, then we can split it into the probability of R given B1. Probability of R given B1. And that's automatically 2 over 18 divided by probability of B1, which is 1/3. If you convert these to multiplication, we have 2 over 18 times 3 over 1 times 3 over 1. So we do that very well. 3 here, this gives 6. So we have 2 over 6, 2. Okay, so everything amounts to 1/6. 1 over 3, right? 2 over 6, which amounts to 1 over 3. So everything equals 1 over 3. So we are going to determine the probability of R, that is the probability of Z, given B1. So determine the probability of Z given B2. It's the same way, similar way. So the probability of Z given B2, probability of Z given B2 will definitely be what? The probability of Z intersection B2 over the probability of what? Probability of B2. That will give probability of B2 or the probability of R intersection B2. But we can determine that from the information given. How many reds are we having there? We are having one red. One that will be 1 over 18. 1 over 18 divided by the probability of B2. The probability of B2 given from the question, that's 1 over 6. Right, 1 over 6. And to multiplication, we have 1 over 18 times 6 over 1. 6 in 18, that's 3. So we have 1 over 3. We have 1 over 3. This 1 over 3 as well. 1 over 3 here as well. We are going to determine that. So we also want to determine the probability of R given B3, and that's also the probability of R intersection B3 over the probability of B3. And the probability of R intersection B3 can also be derived from our information, which is definitely what? 5, because we are having 5 times 5 over 18 divided by the probability of B3 that we given to be what? 1 over 2. 1 over 2. So to multiplication, you have 5 over 18 times 2 over 1. 2 is 18, that's 9. So we have 5 over 9. We have 5 over 9. So that's give us 5 over 9. So we can now be able to get all our parameters. So we can now plug it into our formula for total probability. So our formula for total probability, which is P of R, will now be equal to what? Well, let's recall before we plug it into it. Probability of B1 times probability of R given B1 plus probability of B2 multiplied by the probability of R given B2 plus probability of B3 multiplied by probability of R given B3 So now let's plug it into our formula. So what is our probability of B1? Our probability of B1, that's 1 over 3 times probability of R given B1. We've gotten it from here. Probability of 1 R given B1, that's 1 over 3. 1 over 3. That's 1 over 3. So we also have the probability plus, that will plus the probability of B2. Probability of B2 is 1 over 6. 1 over 6 times probability of R given B2. Probability of R given B2, we have done it as 1 over 3 plus the probability of B3, which is given as 1 over 2. 1 over 2. Probability of B3 is given as 1 over 2 multiplied by probability of R given B3, which is 5 over 9. Which is gotten as 5 over 9. 5 over 9. So if we sum this together, we do that very well. We should be getting 4 over 9. Should be getting 4 over 9 as our final answer, that is as our total probability. So in the next lesson, this will bring us to the end of this lesson. In the next lesson, we'll be moving to some other aspect of probability. So if you're here to subscribe to the channel, kindly make sure you do that, and make sure you like, you comment, you share the video with those that will find it helpful. Tutor Bosun is here. Thank you.